Hello everyone, myself Dr. N.C.H. Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to today's session on some problems on analytic and harmonic functions. Now today I am going to solve some problems on analytic function as well as harmonic function. So using CR equations we can check whether the given function is analytic or not. Similarly, by using the definition of analytic function also we can check where the function ceases to be analytic. Similarly, harmonic function. A function u is said to be harmonic if it satisfies the Laplace equation del square equal to u equal to 0. So, we can verify whether the given function is harmonic or not by finding the second order partial derivatives and adding the both partial derivatives with respect to x and y. We can check whether the given function is harmonic or not. Now coming to the first problem, find where the following functions ceases to be analytic. Ceases, that means fails to be analytic. So that means where the function w fails to be analytic. We need to find out that point. So first one, w equal to 1 by z. Now what is the definition of an analytic function? If the derivative exists in the neighborhood of that point, then it is said to be simply analytic. So let us find the derivative of this. So w equal to f of z, which is 1 by z. Let us differentiating, we get f dash z equal to minus 1 by z square. Since z is in the denominator, this is for z not equal to 0. So if we take any value other than this 0, yes, the derivative exists. So f dash z exists for all values of z except z equal to 0. So at z equal to 0, f dash z tends to infinity. That means derivative doesn't exist. Derivative does not exist. Therefore, this function w equal to 1 by z ceases to be analytic at z equal to 0. So, if the derivative exists at all the values of z except for z equal to 0. Hence, the function is not analytic at z equal to 0. That is the first one. Similarly, second one. Here w equal to z by z minus 1. So here f of z is z by z minus 1. So if you differentiate this, we need to apply u by v rule, and in denominator we get z minus 1 whole square and some function of z here. So again, in denominator we have z minus 1, and this is valid only for all values of z except for z equal to 1. So for example, if you want to find this derivative, so denominator into derivative of numerator 1 into 1 minus numerator into numerator z into derivative of denominator is 1. So this is z minus 1 minus z by z minus 1 whole square. So simply minus 1 by z minus 1 whole square. So again here, this w equal to z by z minus 1. So f dash z exists for all z except z equal to 1. So the function is not analytic at z equal to 1. And coming to the third problem, z cube minus 4z plus 1. W equal to f of z cube minus 4z plus 1. Clearly this is a polynomial equation. And here we have z in the numerator. Even if you differentiate it, we will get z in the numerator itself. 3z square minus 4. And this is valid for all z. Hence, the function w equal to z cube minus 4z plus 1 is analytic everywhere. And the fourth one, z plus 2 by z into z square plus 1. W equal to z plus 2 by z into z square plus 1. So, to find the points at which the function ceases to be analytic, that means isolated points. So, to find the singular points, equate the denominator to 0. Equating denominator to 0. Z into z square plus 1 equal to 0. So, z equal to 0 or z square plus 1 equal to 0. That means z square is minus 1, z is plus or minus I. Therefore, the given function is not analytic at z equal to 0, comma plus or minus I. So, at these points, the given function is not analytic since the derivative doesn't exist. Now, the second problem, show that the function u is harmonic. So, consider the given e power minus x, x sin y minus y cos y. So, a function u is said to be harmonic if u satisfies the Laplace equation del square u equal to 0. That implies dou square u by dou x square plus dou square u by dou y square is equal to 0. We need to check this condition. So, for that reason, let us find dou u by dou x, the first and second order partial derivatives of u. Now, first dou u by dou x with respect to x. So, we need to apply uv rule. E power minus x with respect to x. So, sin y. Here minus, we treat y as constant. So, 0 plus x sin y minus y cos y into the derivative of first minus e power minus x. So, this is simply sin y plus e power minus x into y cos y minus x sin y. So, here we have applied uv rule. The first function into derivative of second plus second function into derivative of first. And here we have negative sign multiplying with this term. We get y cos y minus x sin y. Now, again differentiating with respect to x. We get dou square u by dou x square. Again with respect to x. So, here sin y is constant. Derivative of e power minus x is minus e power minus x into sin y. And again here we need to apply uv rule. The first function, integral of second, 0 minus with respect to x. So, sin y plus y cos y minus x sin y into the derivative of first e power minus x. Now, again simplifying this, minus e power minus x sin y. Here minus e power minus x sin y again minus y cos y e power minus x plus x sin y e power minus x. So, finally, this is x sin y e power minus x minus y cos y e power minus x minus 2 e power minus x sin y. So, this is the second order derivative of u with respect to x. Similarly, we need to find the second order derivative of u with respect to y also. We have u equal to e power minus x into x sin y minus y cos y. X sin y minus y cos y. Now, let us differentiate this with respect to y. Then e power minus x is constant. Derivative of this function with respect to y, x constant cos y. Here we need to apply uv rule. Minus y into derivative of cos y is minus sin y minus cos y into derivative of y is 1. So e power minus x, just simplification, x cos y plus y sin y minus cos y. So this is x cos y, y sin y minus cos y. This is the first order derivative dou by dou y. Again differentiating with respect to y, we get the second order derivative of u with respect to y. Again e power minus x is constant. Now the inner function here with respect to y, so minus x sin y, and here uv rule plus y cos y plus sin y minus cos y derivative is minus sin y, so plus sin y. So after simplifying, minus x e power minus x sin y, y cos y plus y cos y e power minus x, here 2 sin y plus 2 sin y e power minus x. So this is the second order derivative of u with respect to y. And here this is equation 1 and this is equation 2. Now adding 1 and 2, dou square u by dou x square plus dou square u by dou y square is equal to, now dou square u by dou x square, x sin y e power minus x minus y cos y e power minus x minus 2 e power minus x sin y plus dou square u by dou y square, the previous slide, y cos y e power minus x, y cos y e power minus x plus 2 sin y e power minus x minus x e power minus x sin y. So plus x e power minus x sin y minus plus minus plus. That implies dou square u by dou x square plus dou square u by dou y square is 0. That implies del square u is 0. Therefore, u is said to be harmonic. Since u satisfies the Laplace equation, u is said to be harmonic. So to verify whether the given function is harmonic or not, just find the two second order partial derivatives of u with respect to x and y and add them. If the result is 0, simply del square u equal to 0, hence u is harmonic. Otherwise, it is not harmonic. Similarly, one more problem here. U equal to x square minus y square and v equal to minus y by x square plus y square. Show that both are harmonic. So the same procedure we follow. Let us find dou u by dou x, 2x, dou u by dou y, minus 2y, dou square u by dou x square. So again differentiating 2, dou square u by dou y square, minus 2, adding these two, dou square u by dou x square plus dou square u by dou y square is 2 minus 2, 0. That implies del square u is 0. Therefore, u equal to x square minus y square is harmonic. This is, since the function is simple, the derivatives are simple and we can prove this. Now, coming to the second one, v equal to minus y by x square plus y square. Now, let us differentiate v with respect to x first. So, minus y constant, dou by dou x of 1 by x square plus y square. So, by differentiating this, we get so 2xy by x square plus y square whole square. Now, again differentiating v with respect to x, dou square v by dou x square. So, what is dou v by dou x? 2xy by x square plus y square whole square. So, we have dou v by dou x is 2xy by x square plus y square whole square. Now, again differentiating with respect to x, we get 2y constant, dou by dou x of x by x square plus y square whole square. Now, first find this using u by v rule. So x square plus y square whole square, denominator whole square, so power 4, denominator into x square plus y square whole square into numerator derivative with respect to x, 1 minus numerator into denominator derivative, 2 into x square plus y square, and again inner function derivative, 2x. So that is equal to 2y constant. Next, in numerator I can take x square plus y square common. Then one more x square plus y square in the first term minus 2 into 2, 4x square by x square plus y square power 4. So this is equal to this here 3 times, and in numerator is y square minus 3x square by x square plus y square whole cube. This is dou square v by dou x square. Now we have v is minus y by x square plus y square, minus y by x square plus y square. Let us differentiate with respect to y now. Dou v by dou y, uv rule, x square plus y square whole square, the denominator into numerator derivative with respect to y, minus 1, minus numerator into denominator derivative with respect to y, 2y. So this is minus x square minus y square plus 2y square by x square plus y square whole square, which is y square minus x square by x square plus y square whole square. Now to find the second order derivative, again differentiate this with respect to y, dou square v by dou x square. Now the denominator whole square, x square plus y square power 4, denominator into x square plus y square whole square into numerator derivative with respect to y, 2y, minus now numerator into denominator derivative, which is 2 times of x square plus y square, and again inner function derivative with respect to y, 2y. So by simplifying this, we get x square plus y square we can take common, and 2y also, then one more x square plus y square here. So this term x square plus y square and 2y, this has been taken out. So what is remaining? Minus 2y square plus 2x square by x square plus y square power 4, and this 3 times cancel, and now 2y into 3x square minus y square by x square plus y square power 3. So we have obtained the both second order partial derivatives of v with respect to x and y. So this is equation 1 and this is equation 2. Now let us add these two. Adding equations 1 and 2, we get the equation 1 is dou square u by dou x square. Equation 1 is dou square v by dou x square, and equation 2 is dou square v by dou y square. So that is equal to, now let us go back, dou square v by dou x square, 2y into y square minus 3x square, 2y into y square minus 3x square by x square plus y square whole cube, and equation 2, 2y into 3x square minus y square, 2y into 3x square minus y square by x square plus y square whole cube. So here LCM x square plus y square whole cube and 2y cube minus 6x square y plus 6x square y minus 2y cube. So that implies del square u is 0. Sorry, del square v is 0. Therefore, v is harmonic. Hence, to check whether the given function is harmonic or not, simply find the second order partial derivatives and add them. So today in this session, we have solved some problems on analytic and harmonic functions. So to deal with these analytic and harmonic functions, the first thing is you should know how to find the partial derivatives. Partial derivatives. So that means you should know the partial differentiation. Then know the definition of analytic function and harmonic function, and if there are any conditions to check those, for example, the CR conditions to check analytic function, and Milne-Thomson method to find the analytic function when real and imaginary part, any one of real and imaginary parts is given. So simply, without knowing the partial derivatives, you cannot check this, you cannot deal with these functions. So this is for today's session, and we will meet in the next session. Thank you.